Hey guys, so this is one of three problems that I have prepared for you for midterm review. So the midterm is going to cover chapters 8 through 10, and so this is chapter 8. So the types of problems that I've picked for you, I think are representative of things that are either subtle about the chapters or something where I believe that details have been glossed over in the book. So I'd like to go over problem 8.31. And what I like about this problem is this is concerning two particles in a repulsive inverse square potential. So the problem asks you to do two things. So one, show that no negative energy states exist in the center of mass frame. And as the book discusses, negative energy states in this context correspond to bound states of a system. Two, show that all E greater than 0 states are hyperbolic. My own aside here is that we can also show that E is equal to 0 states are going to be parabolic. Now, this problem is a little bit more subtle than how it first appears, and it builds on everything that you've done with attractive inverse square potential problems, such as a gravitational field or having two charges that are electrically attracting each other. So the setup for this problem is pretty straightforward. It's going to follow what you've done before. Again, for attractive potentials. First step is to identify what are the radial forces, such that we can write down the expression for the energy so that we can solve the first part of the problem. Third, this will allow us, by knowing the radial forces, to write down a radial equation, which is going to be a differential equation for the evolution of the radial coordinate, which we can then solve. And finally, look at ranges for the parameters in the problem. And these parameters are going to include the eccentricity of the orbit, because we are dealing with these orbital type problems. So overall, here's the trick where you can do this problem a little bit simpler. Gamma, which shows up in the numerator for the radial force, throughout the book has been taken to be attractive, and so it has a minus sign in front of it. To make it repulsive, all we need to do is anytime we see gamma, replace it with negative gamma. So what that means is that one, the radial force is going to be equal to gamma over r squared, with the constraint that gamma is equal to gamma is just greater than 0, such that we know this is going to be repulsive. What that implies about the energy for the system is that it's going to be equal to the kinetic energy, and this is greater than or equal to 0, plus the potential energy given by the potential that generates that force, which is gamma over r. And now we know that r is greater than or equal to 0 and gamma is greater than 0. So this implies that this whole expression is greater than or equal to 0. So that shows the first part of the problem, that there cannot exist any negative energy states because the potential itself is not negative and the kinetic energy itself is not negative. Therefore, no negative energy states because those two energies add to give the total energy of the system. Very nice. So you've seen the radial equation in the textbook before. Basically, the idea behind the radial equation is that you can solve Newton's equation easier for these types of problems if you make the substitution r is equal to 1 over u. So you can consider u to be a function of r, which is just 1 over r. This is just a trick for solving these sorts of differential equations such that it becomes apparent how a solution will come out. The reason why you would want to consider such a solution is because in the differential equation expressed in terms of r, you see expressions of 1 over r to some power that end up being turned into polynomials of u, and polynomials in differential equations are typically easier to solve. And so, like I said before, the main thing that we are doing is taking gamma to minus gamma wherever we can, and therefore that makes solving for the radial equation easier. In terms of u, the radial equation becomes this. Here, mu is the reduced mass, and L is the angular momentum of the system. What this allows us to do is solve the differential equation in the same way that it's solved in the book. One can substitute in W is equal to U plus gamma, gamma mu over L squared. And you end up with W prime is equal to minus W. That's how you go about solving the differential equation. Because the orbit comes back onto itself, this is why you end up with a factor of cosine, where the argument of cosine is offset by a phase factor, depending on where you start on the orbit. We don't need to go into this here because it is given in the book, but I wanted to clarify that in case that was confusing in the book. So all in all, again, you're really just where you see gammas, you are taking that to minus gamma. And so you didn't even need to write down a differential equation and solve it. You could have just taken the solution given in the book and done that substitution, noting that C that shows up in the book depends on gamma. Cool. So the big difference here is that the denominator is going to be off by a minus sign from what it was before. So an equivalent way of writing this is this. So there's just going to be a two relative minus signs difference in the denominator for the expression for r. And that makes all the difference in terms of the behavior of this system. So just as in the book here, C is equal to L squared over gamma mu. And this is going to be greater than 0, again, because the reduced mass and gamma are both greater than 0, and L squared, because the squared quantity, is inherently greater than 0. And epsilon has to be greater than or equal to 0. Note that we've set the phase delta equal to 0 in this problem, and that's just a choice of coordinate system that we've made such that the initial place in which we start our trajectory is lines up in that coordinate system with the choice that we made. Now, the expression for the energy does not change when we take gamma to minus gamma, and that's because the energy is proportional to gamma squared. So E is equal to gamma squared mu over 2L squared, epsilon squared minus 1. So you'll notice that we haven't broken things into kinetic and potential energy here. That's what we had before. We made an argument the energy had to be positive. Using that expression, now we are able to solve for what the energy is in its totality without any reference to a kinetic energy or to the repulsive potential. Now recall, like we already solved with the kinetic energy and the repulsive potential analysis on the energy is forced to be positive. This expression, if we plug in epsilon is 0 or epsilon is anything less than 1 actually, is going to be negative. What that means is we are forced to have a constraint on epsilon. And this is the subtlety in the problem that I wanted to share with you guys, that like it's not just completely copy paste going from one situation to the other. Basically, the implication here is that epsilon has to be greater than or equal to 1. Now, for this problem, if epsilon is equal to 1, we have the energy is equal to 0. This is the same as what you've seen in the book for showing that you'll get a parabolic trajectory doing this. And the problem has asked us to only consider cases in which E is greater than 0 and show that those are all hyperbolic trajectories. Now, the only other case is epsilon is greater than 1, and that implies that E is greater than 0. What we're going to see is that R times epsilon cosine phi minus 1 is equal to C by manipulating the expression for R. And what that means is that we can start figuring out what the trajectory is by plugging in the appropriate expressions for X and Y. How do we solve those? Well, we know the following. R is equal to square root x squared plus y squared. And R cosine theta is equal to x. Sorry, phi. R sine phi is equal to y. Therefore, this expression becomes epsilon x minus square root x squared plus y squared is equal to C. We can then bring the square root onto one side of the equation, everything else onto the other, such that we can square things to get a polynomial expression. I'm going to leave this out, but what this implies is the following. This equation can be rewritten in the form x minus d squared over a minus y squared over b squared is equal to 1. And that should be an a squared, my mistake. For reference, if you want to do the algebra, a is equal to c over epsilon squared minus 1, b is equal to a root epsilon squared minus 1, and d is equal to a epsilon. This is the equation for a hyperbola. The reason being is that there's a relative minus sign between the x squared over a squared term and the y squared over b squared term, and a squared and b squared are not necessarily equal to one another. All that the d does is offset the x coordinate. So what I mean by that is the origin of the hyperbola ends up being offset. If you wanted to draw a graph of this, which is something that the problem also asks for, if I have x, y axes, so particle 2, which is very massive, would be centered at the origin approximately in this problem, and particle 1 would be taking the hyperbolic trajectory, with this distance being a plus d between particle 2 and the smallest x position of the hyperbolic trajectory. Great, so again, the point of this problem, repulsive potential acts a little bit differently than an attractive potential. And this stretches a little bit of what you've already seen and gotten comfortable with by just doing the attractive potential problems. All right, guys, I will see you in the next video.